So this is log of the base I want of the top divided by log of the base I want, which is base 2 of the bottom. And by doing that, now log base 2 on 16 is going to be 4, right? Because 2 to the power of 4 is 16. So therefore I can replace this with log base 2, right? This will be log 2 of x. I can replace the log base 16 of x with log base 2 of x over 4. And then you can solve this equation. So now you have everything the same base. So then I can multiply across by 4. So this is 4 log 2 of x plus log 2 of x is 12. Right? And then you can collect like terms. And I just made this question up, so the numbers are a little messy, but they're not too bad. Right? So like I collected like terms, divided through the 5, and then I can go to exponential form. Right? So then I can, from here I can change the exponential, so it'd be like 2 to the power of 12 over 5 is x. And that would be your, that would be your answer. So that would be an example of change of base, using your change of base formula, like in a question, if this was the original question right here. Can kind of do it like that. Okay. Did you guys want to try a change of base equation? It's up to you, or we can move on. I know Reem wanted some compound interest, and Sivert wanted 331. Yeah, do you, where did you get to, Yusria? Did you get to the, like you see, you got to the equation here? Like, were you good for the setup? Okay, Sibra, are you there? I can talk about your question. You wanted 331.25. All right. So quickly, Yusria, how it worked was, I was saying you need a change of base. So for this question, let me kind of zoom in here if this helps you see it a bit. I needed a change of base. So for that question there, I can't apply my logarithmic properties because I don't have the same base. So what I did was I said, okay, I'm going to go to base. I have a base of 16. I'm going to make this a base of 2. So I went ahead and I did my change of base formula, and I got log base 2 of x over 4. Right? And I sub that in to this equation here. I sub that into this equation there, and then I multiplied across by 4, collected like terms, and then switched to exponential, and I got my answer. It was a little bit messy, but that is the answer. Okay, sure. Let me get to Sibra's question, and then I can do that. So, and I owe Reem a question too. So Sibra, you're 331, number 25. All right. So I got another textbook here, Sibra. I just want to make sure it's the same question. So this is what I got for number 25. It's 3 to the x is 2 to the x minus 1. Is that the question that you have as well? Okay, so this is a good question. So with something like this, Sibra, you want to solve. There's actually 2 ways you can do it. Here, I'll do it maybe the more straightforward way. One way you could do it is I could take the log of both sides of the equation. It could be any base, but we can just take log base 10. So if I take log both sides of the equation, automatically those x's drop down, and it becomes x log 3 is Don't forget, this whole thing is to the x minus 1, so that whole thing drops down, becomes x minus 1 log 2. So that's like one way you could go about doing it, but it's still not easy because I have to solve for x, but I can't get at this x value unless I distribute this log 2 into the brackets, right? Because you sort of can't get at that value unless you break it apart. So this becomes this, right? And now the goal is to solve for x, so I'm going to bring the x's to one side. Log 2. And then I can factor out an x. So I get log of 3 minus log of 2 is negative log of 2. Are you following so far, Sibra? You can ask as I'm going through it. It's a little delayed, I think, but... Are you able to follow along with this? Okay, so then divide it out, and the answer is negative log 2 divided by log 3 minus log 2. And that's there's your answer. So that's one way you could do it, is just take the log of both sides. I think when I answered this earlier, I might have done it a different way. You might not like the different way. I'll show you another way that you could do it. So that's one solution method. Another way you could do this question is you could write this as 3 to the x. I could go 2 to the x times 2 to the negative 1, right? I could do my exponent rules sort of in reverse. So break it apart. And then it's still not that nice, but then I could divide by 2 to the x. So I could bring the 2 to the x's together. And this would be a half. And then I could go like this, to kind of take the exponent out. And then I could take the log of both sides. So then I'd have log of 3/2 x is log of a half. So you could do that as well. I'm not sure. I think the first way is a little cleaner. But this will give me the same answer. This is log of a half divided by log of 3/2. Oops. 3/2. So you could do it that way as well. I made a little mistake. There we go. So I could do it that way as well. And you'll get it looks different, but it's the same answer as we have here. Yeah, I thought so. Yeah, this way's a little bit weird, but it does work that way too. Okay, so there's 327, number 3, or 331.25. I can do 327.32. Reem, are you still there? Because I owe you that compound interest question as well. 327.32. Right. So here's 327.32. Ibrahim, you there? I can go through it with you. 327. Oh, the epidemic question. All right, so you wanted this epidemic question. What is this? 20,000 over 10 plus 1990 e to the negative 6t. All right. I should get some WD-40 for this chair because it's super squeaky. All right. Okay. Okay. You need help with probably part B, right? You know how to plug the numbers in, I'm assuming. You need help with the graphing? Okay, so, with this one, Ibrahim, it's a little bit weird. You've got this equation. Let me zoom in on it a bit. Actually, let me see if I can do this. Oh, that looks nicer. Oh, I wish I could do that in class. Look at that. Legible. Okay, so with this here, Ibrahim, this is measuring like an epidemic. T is measured in time. It starts at year 2000, blah, blah, blah. They want you to graph this. This is, we'll kind of talk about this tomorrow. This is like we'll work with these a little bit more, but the idea here is as time goes to infinity, right? Like if you have your axis, let's say this is my axis here. Let's say this is time. Hey, Ahmed Amar. Hello, Amar. How are you? How's it going? I'm helping my 12 functions class. You're probably doing well in university, I bet. Oh, yeah. Yeah, me too. Amar was one of my best students. Taught him in grade 10, and I think I taught you virtually grade 12. Yeah. We're... All right, so with this one here... with this one here, Ibrahim, you can hang out here, Amar, if you want. But I'm just going through my 12 functions class, has some questions. But I hope you're doing well. I'll bet you're doing well. Ibrahim, with this question here, what happens is it's this epidemic, but as t goes to infinity, can you see that this will tend towards 0? Thanks for dropping in, Amar. Oh, that's funny. Ibrahim, do you see this? So, do you get like as t goes to infinity, this will approach 0? Like, can you visualize that? Right? Because what's going to happen? This is 1990 over e to the 6t. So this is obviously going to be approaching infinity very, very fast. And this will be, so the whole thing will be approaching 0. So the idea here with this is as t gets really, really large, there's a point to this I'm getting to. P at t is going to approach 20,000 divided by 10. It's going to approach 2,000. So this function here has like a horizontal asymptote at y equals 2,000. So like it kind of, like the epidemic starts at, if you let time be 0, the epidemic starts at 1. Like if I evaluate this function at 0, you actually get 1. So it starts at 1 and then it just like tends upwards like this. Looks good. All right. Am I back? I am back. See, it's kind of like reflecting up, right? Because like this is my normal ln of x function, but I'm absolute valuing the output, so these all get reflected up. Okay. And then, Emre, if you really want to know if you understand it, you could try to graph, like, for instance, log of, like, 0.5 absolute value of x. And then you could also try to graph, like, log of 0.5x with the absolute value on the outsides. Because, like, if you change it to a base of a half, it's not going to look the same. right? You could ask me later, but this is log base a of x when a is greater than 1. And then your other one looks like this. And this is log base a of x when a is between 0 and 1. So remember from when I originally taught logs, they look different depending on the base value. Base of a half is going to look different than a base of like something greater than 1. Right? So if I asked for, Emma, are you following? Is this okay? Okay, yeah. So if I asked for this, like log of a half absolute value of x, actually it would look like this. Like this would be log of 0.5x the absolute value. But something to think about. We can talk about that too. Okay, so there's that one. Okay, now I'm on to this page. What is this? Page 312? Sure. All right, page 312, 38, 41, and 61. 38, 41, 61. Oh, you wanted to see that one, Yusria? Yes, very good. For the other one, you'd reflect the negative. So if I was graphing this, if you absolute value the whole thing, that's your log of that. If I absolute value the whole thing, I'll do it in this color here. It would go, this would all be the same, and then this would reflect up like that. And this would be the absolute value of log of 0.5x. Okay, 312. Okay, I don't have a 312. Did you mean 321? I got 38, 41, and 61. Is that, do you mean page 321, I assume? Whoever asked that one? Oh, maybe not. Also, did you get 2 lines for the answer to the last? Oh, is it from the Sullivan? Is it, what is the questions? Is it the, I don't have a, what's the question? Like, I don't see a 312 on my, like, it's just, there's no questions on page 312 from the Addison, or the Algebra and Trig book. Unless it's from, oh, sorry, you're asking about the Sullivan text worksheet. Gotcha, okay. Yep, let's take a look at that. So, oh, I see. I found it. Okay, I got it here. So for this one here, 38. Oh, yes. Okay. I was talking about this with with Michael, to this class. So for number 38, it asks you what rate of interest compounded continuously will yield an effective rate of interest of 6%. What they're asking in this question is they're saying, like, you have a situation where you are compounding like you want to find out what k value do I have to raise my exponential to such that it's the same as compounding 6% annually. So what you're doing is you're taking your continuous growth model, which is e to the k, and you're equating it to like a traditional compounding model where you compound at the end of the year at 1.06. So what we're doing here is you're kind of like solving this equation for k. So like if I solve this, let me show you what they mean. I just need my calculator. 1 second. I think I have my calculator. All right, I got a calculator. So for this one here, this will make sense once they go to solve it. You want to solve for k. So for something like this, you take the ln of both sides to solve for k. This becomes a ln of 1.06. So you drop down the k. I have ln of e is ln of 1.06. So k is ln of 1.06 over ln of e is just 1. So k equals ln of 1.06. So if you calculate the ln of 1.06, I end up getting k is 0.0582, which is about 5.82%. The reason it's that is you're compounding at 6% a year. So you're saying, like, what's the equivalent growth rate if I compound continuously? So what they mean is, like, someone says, hey, I'm going to pay you 6% for the year for interest. Then you're saying, okay, what would be the growth rate so that if I compute interest continuously, I'll still it'll like be the same at the end of the year, it'll be the same interest rate. And that's only 5.8% because you're computing interest continuously. So like what they're saying here is like if you have $100 invested, like calculated interest continuously at 0.0582, that's going to give you the exact same number as if I take $100 and compute it at 6%. Like this, these numbers yield the same output. Do you get it? Like here, watch, for instance, like if someone says, okay, I have 10% annual rate of interest. I'm gonna compute it at 10% annual rate. What's the corresponding? They use the word effective rate for continuous growth. You take e to the k, you set it equal to 1.10. Right? And then if you go to solve this, you get k is the ln of 1.10. And if you solve for that, you take the ln of 1.10, I get 0.0953. So that's equivalent to 9.53%. Is that starting to make sense? Oh, you're having trouble with the 1? The reason you're adding 1 is if you remember our compound interest formula was 1 plus I to the power of whatever, kt, right? We had that formula. So this is your base. So you're equating the bases. So my other formula was P at t is P naught e to the kt. So you're kind of like taking e to the k and setting it equal to your interest rate here. These are different k's, by the way. So it's not the same k. But you're taking your e to the k, you're equating your bases pretty much. And you're saying for what value of k are the bases the same. So what you're really doing is you're taking 1 plus I and you're setting it equal to e to the k. Right? My I value originally was just 0.10. So 1 plus 0.1 gave me the 1.10. And previously it was 6%, so it was 1 plus 0.06. Gave me the 1.06. Have I cleared that up? Yeah? Okay, good. And then, like, if you changed it, just to, I don't want to confuse you, but let's say you had 10%, but it was compounded monthly now. What you would do is this would be equivalent, this would be 1 plus I. What's my I value? It's going to be 1 plus, this time it's 0.10. It's not, because we were doing annually, we were dividing by 1. Now I have to divide by 12 here. So this will end up being 1 plus 0.10 divided by 12. This ends up being 1.0083, right? And then, so if I want to compute the effective rate of interest, I'd have to take that value and set it equal to e to the k. And then I'd have to solve. So you take the ln of both sides, and I get that's my k value. So if you compute that, I get 0.0082. So in this case here, it's like 0.82%. Like per thing. Okay, so that was 30, what was that? All the way down here. That was 38. You wanted 41 and 61? Okay, so for 41, all right, great. 41 is time required to reach a goal. So for number 41, you have an initial investment of $10,000. So right away, P naught is 10,000. You want it to go to 25,000. So P at T is 25,000. The rate of interest is 6%, compounded continuously. And they want to know how many years would it take. So in this one, you want to solve for T. So right away, they use the word continuous growth. So because it said continuous growth, I go right to my continuous growth model, e to the kt. P at T is 25,000. That's what I'm ending up with. I start off with 10,000. It's continuous growth, so I have my natural base of E. This is 0.06 times T. So now that you've subbed everything in, you're solving for T here. So divide across by 10,000, you're going to get 2.5 is e to the 0.06 t. And then you take the ln of both sides. So you end up getting the ln of 2.5 is 0.06 t. And I get t is the ln of 2.5 over 0.06. So I'm getting 15.27 years for this question. Does that make sense for this one? For 41? Okay, there's 41 and 61. Yeah, the answers are posted as well. There's a worksheet with posted answers. Yeah, it's like there's 3 worksheets. One's last night's homework, tomorrow's homework, and then the homework for both are posted. But for 61, they tell you you have the rate of inflation. The rate of inflation is 2%. So that's given to you in the question. The rate of inflation is 2%. They ask you how long until the purchasing power is cut in half. So kind of interesting question. So they want to know with this inflation, if the rate of inflation is 2%, that means you're only going to get 98% of what you had every time. So if I let P naught be like the initial amount of money that I had, so maybe it's $1,000 or $100, whatever, they're asking how many years would it take, so I raise that to the power of T such that I'm only left with half of what I had. So if the rate of inflation is 2%, how many years has to go by until your purchasing power is cut in half? Right? Whether it's $1, $100,000, or $1 million, when does that amount get cut in half? Does this equation make sense? And anyone else can ask as well if they're curious about this question. This is 61 from the compound interest worksheet. All right. So just like what we did, the doubling your investment, whatever, those cancel. So that didn't matter. And now you're just solving this equation. So then you take the ln of both sides. You could take the log of both sides too, by the way. Doesn't matter. That T drops down. Right? And so the answer is ln of 0.5 over ln of 0.98. So I'm getting I'm getting 34.3 years as my answer. So it takes about 34 years to cut your purchasing power in half if the rate of inflation is only 2%. So there's that one. That's a good question. All right. Are there any other questions? I know Reem had asked for compound interest, but then I kind of lost. I think Reem might have taken off. Are there any other? No, it does not. Like if you take the log of both sides, you actually get the same answer. Just to show you, here's like 0.98. If I take the log of both sides, it's going to be log of 0.98t is log of 0.5. So t is going to end up being here log of 0.5 over log of 0.98. And if you put that in your calculator, you'll get the same answer. If I take log of 0.5 divided by log of 0.98, I again get my calculator. You can check it out yourself too. I get 34.31. So same answer as before. Oh, I answered your compound interest question. Okay, good. I didn't know if I had answered it. Okay, are there any other questions that anyone needs? Oh, okay, you're asking about 26. Let's see, Yusria. Ln of, okay, this one here. Here, I'll redo it, Yusria. We can talk about it some more. I'll just copy that equation. Let's take a look at it some more here. All right. So with this one here, what I was saying when I was talking about graphing this is I got two lines because if x is greater than or equal to 0, right? If x is greater than or equal to 0, then this equation just becomes the ln of x. Right? If x is greater than or equal to 0, you just drop the absolute value and it looks like this. Do you agree with that, Yusria? Actually, I should not say greater than or equal to 0. I should say greater than 0. It can't be equal to 0 because it's undefined at 0. So if x is strictly greater than 0, our graph looks like that. You would just drop it. But now, normally with this would be it. We'd be done. But now, because I have the absolute value on this, we can now take in negative values. So before these values would have normally been undefined. But now I can take the ln. Okay, yeah, let me just take a side note. The reason it's undefined at 0 is if you take the ln of 0, that's equivalent to asking log base e of 0. And what that means is that's the exponent. What do I have to raise my base to get 0? And there does not exist a value. Like there's no x value that you can raise this to make it 0. It's impossible. Right? So that's why you saw when we graphed our logarithmic functions, it always has a vertical asymptote at 0. If you look at all the logarithmic functions we've graphed, they all have vertical asymptotes at 0. Right? Whether I'm graphing log a of x or I'm graphing from a decay one, like either of our logarithmic functions, they always have vertical asymptotes at 0, right? And like on our quiz or whatever, you can never. This is always like undefined, right? You can never have your logarithm acting on 0 as an input or any negative number as well. So, Yusria, back to your question. Now that we have the absolute value on it, this is going to be the same as ln of 1. So if I ask for the ln of negative 10, it's going to act exactly the same as it did at 10. This will act exactly the same it did at 1. So if I ask for the ln of negative 100, it's going to output the same as it did for ln of 100. So my point is that if I pick a value, let's say I pick x is negative 1, it's going to act exactly as it did over at 1. If I pick a value here, it's going to act the same as it did here, same as it did here, same as it did here. So all these points now are going to be the same. So you end up getting like this idea. Because whatever was good here, maybe this is at x equals 10. It's going to output this. On the exact other side at x equals negative 10, it's going to output the same thing. Because you're hitting it with an absolute value, the outputs are the same for that same input. See here? So it makes it symmetric. Does that explanation? Okay, you got that. Okay. Another way you can view it, Yusria, is that if x is less than 0, then the ln of the absolute value of x is equal to ln of negative x. And that's just a reflection in your y-axis as well to get that second line. Like you can view it that way if you're looking for like another version of this. Could do that. No problem. Is there anything else I could help you with? Sorry, sir. No, not a problem. 66. Okay, that was from a while ago. Where is that? 66. This one. For sure. Okay, Yusria, for this one here, 66. We can look at it again. It's just a change of base. right? This is equal to log base e of m. This side of the equation is log base 10. So the only thing I do is I do my change of base to a base of 10. So log of the base I want of the top divided by log of the base I want of the bottom. But this is exactly equal to log of m. Like, it's just a notation change, and this is exactly equal to log of e. That's what we have there. Okay, no problem. All right, and you wanted, who is Hyatt Adam? Who am I talking to here? Number 7B. 7B. Hyatt. Teacher Hyatt? All right. Let's take a look. So for 7B here, what did you want in 7B? Population of a city, N is the population of the city and T is time in years. I see. If the okay. So this is the Sullivan. This is Sullivan, page 325. If N is the population of a city, so that must be P naught is N. T is the time in years. Express N as a function of T. So for this one, KT. N e to the KT. Now what do they want here? If the population doubles in size over an 18-month period and the current population is 10,000, what will the population be in 2 years from now? Okay. So with this question here, let me see. Okay, I don't get the point of A. It's kind of just all set up here for A. For 7B, they say the population doubled in size. So if the population doubled in size, they say it happens, T is measured in years. So they say this happened in 18 months. That's 1.5 years. So I know that P at 1.5 is equal to 2N. Is that okay so far? So I know that 2N equals N. Sure. In the question, they say that the population doubled in size over an 18th month period. So that means that the population after 18 months, so 18 months expressed in years is 1.5. So the population at 1.5 is equal to twice the original population. So whatever the original population was, it's 2N now. This would be K times 1.5. Do you see that? Okay, so the n's cancel, and I get 2 equals e to the 1.5k. the whole reason we have this information is so I can solve for the growth rate, the k value. Then I sub that in to solve for the next part of the question. So now I can solve for the growth rate here. So now that I've equated these cancel. I can now take the ln of both sides. So I get the ln of 2 equals 1.5k, in which case k is like ln of 2 over 1.5. So if I take the ln of 2 and divide it by 1.5, I'm getting 0.4621 approximately. Are you good? Are you good so far with what I'm doing? Do you follow what I'm up to so far with this? Okay, so now that doesn't answer the question though. They want to know what's the population at 2 years, but now I have my population formula. They're telling me that I start off with 10,000 people. I know it's e to the 0.4621t, right? So now I actually have an equation. I started off with 10,000 people. I've got this growth rate that I solve for. So now they want me to find this after 2 years. You let t be 2. So this becomes 10,000 e to the 0.4621 times 2. And that'll give me the population after... Wait, no. Okay. Ask away. Just tell me what you're having trouble with. Right here. So what I did was I took the ln of, let me make some space here. I took the ln of both sides, so it's going to be ln of 2 equals ln of e to the 1.5k. That's the step in between. And then that 1.5k will drop down to here. And then the ln of e is 1. So it became ln of 2 is 1.5k. Good. So like once you found that k value, then like I have my model here. Like I have the exact growth model of this function. So now they wanted at 2 years, and the initial population was 10,000. So I just let the end value be 10,000. Sub the numbers, you get 25,198.51. Is that okay? Okay, great. Okay, are there any other questions? So for 32, you took up, I got Piet. Yeah, let's take a look at that. Yusria, that was the one that Ibrahim was asking, the and epidemic one, right here. Here, I'll do it with you here. We can kind of do it together. Okay. So P at 0 is going to be 20,000 divided by 10 plus 1990 e to the 0, which is 20,000 divided by 2,000. Is that right? And that's going to equal 10. What did I say? Did I say 1? Oh, it's 10, Yusri. I was off by a 0. Yeah, it is 10. You're right. That should be a 10. Let me find that question. That'll be a 10. Okay, very good, very good. Is there anything else I can go through? Something that you guys wanted to talk about that you need help with logarithms, exponents, or any other math questions from the course? All right. Okay. All right. I get. Oh, so the graph's the same, just y. Oh, yeah, the graph's is the same. It would just start slightly higher. Like, yeah, it just starts slightly higher. It starts at 10, but yeah, it looks exactly the same. Nothing changes. It yeah, it's still the horizontal. My horizontal asymptote of 2000 was still correct. So it still has a horizontal asymptote at 2000, like a one-sided one. Yeah, like notice with this graph, the time, anything in these quadrants make no sense, right? You never have negative time. You never have negative like population. So all of these are out. The only one that makes sense is that sort of quadrant there. 30119, sure. So you see with this one here, this is a transformation question. So what you want to do is look at your y equals 2 to the x function. This is y equals 2 to the x. And then what we're going to do is you're going to apply the transformations to them. So my first transformation is the shift. This is going to be a shift 1 unit to the right. So notice if I let x equals 0, y equals 2 to the x minus 1 equals 2 to the negative 1, which is a half. So what happens is your y-intercept goes down. So this would be a graph of y equals 2 to the x minus 1. Does that make sense? Because visually what you're doing is you're moving everything over. So like that's where it hits. These values all get shifted over. So it looks almost like the graph is being pushed down, but it's actually being pushed to the right. So this is my graph of y equals 2 to the x minus 1. Now what we want to do next is I want to shift this over or down. This is a vertical shift 3 units down. So now you're going to go here. And then what I have in blue is going to be the graph of y equals 2 to the x minus 1 minus 3. Now, just to make sure I hit everything at the right spot, if you let x equal 0, this becomes y is 2 to the negative 1 minus 3, which is like a half minus 3. So the y-intercept is going to be equal to, this would be, this is over 3, so this would be minus 5 halves here. That'll be minus 5 halves. So it's like somewhere down here. So when you do your graph, it'll look like this. And this is the horizontal asymptote of minus 3. Does that make sense, that graph? Did you want to try some of them with me? The horizontal asymptote's minus 3 because, forget the shift. If I just give you this has a horizontal asymptote of 0. This has a horizontal asymptote of 0. If I ask you to graph 2x minus 1, you're taking the output of the function of your parent function and you're subtracting 1 on it. So you're going to shift everything over 1 unit down. So now it's going to look like this. Oops. Oops. My program is like, there we go. That'll look like that for this one. This would be y equals 2 to the x minus 1. Right? You're taking your horizontal. Originally, your horizontal was at right? Originally, this is y equals 2 to the x, and then you're shifting everything down, so the horizontal shifts along with it. Right? So it becomes a vertical shift. So for that one there, it was y equals 2 to the x minus 3. So your original horizontal was on the x-axis. Now it's all the way down here at y equals minus 3 versus the one here, which is like y equals 0. Yeah, I was doing the y-intercepts just so I was getting it like at the right value, the right spot. But yeah, these are all transformations. Like for instance, like let's say I have you graph y equals negative 2 to the x. Right? What would that look like? You go to your parent function and you graph y equals 2 to the x. And then you realize that you're just taking your output and you're multiplying by a minus sign. Right? So that's going to flip it, make it look like this. Is that okay? And then like, you could do like, okay, well, what would this look like? Can you graph this? And then did you want to try like that? Yes, very good. Yeah, that would be a flip. Yeah, exactly. That would be a flip in the y-axis because you have your normal function like this, and that would be a flip in the y-axis. You could view it as a flip in the y-axis. It would look like this, but it's actually equal to 1/2 to the x. So it's your decay function, but that's what you got anyway when you did it. Yeah, you got it, Yusri, exactly. So for something like this, this is really equal to negative 1/2 to the x. So you're just going to take your decay function and flip it this way, right? This would be y equals negative 2 to the negative x. Right, and then you could even ask, like, you could ask a question like, what would negative 2 to the negative x, like, plus 3, like, what does that look like graphically, right? And that's just it's just a matter of breaking it up into cases, right, and shifting everything around. And once you get here, you know I'm just adding 3, so it has a horizontal asymptote at 3, if you were to graph it. Yeah, that's it. Exactly. Yep, that's all. And I mean, there's not like a lot of variation on this at that point. I mean, then the only option is either you put an absolute value on the x, or you put an absolute value on the whole thing. But you'd have to have something that would you can do sometimes something like that we've done in class. But those are the only sort of variations on that with exponentials. And then logarithms we kind of already covered as well. All right. Are we good? Did anyone need anything else? Oh, these two? Sure. All right, let's take a look. So for this one, again, it's sort of like the one I had done with, I think with you, Yusri, we were working on, and Emre was the ln of absolute value of x. It's the same idea. There's like two options. Either you're going to graph 2 to the x when x is greater than or equal to 0, or I'm going to graph 2 to the negative x when x is less than 0. Well, when x is greater than or equal to 0, I know what these look like individually. Like the graph of this just looks like this. But I'm only interested in this graph when x is greater than or equal to 0. So what I have in red represents this one. And then over here, this graph is, like we just talked about, this is 1/2 to the x. So this is a decay function, looks like this. So what's happening with this one is when x is less than 0, I'm graphing all of this portion here that I have in purple. So essentially what you're doing is you're kind of superimposing these together. I don't know if you can see the graphic I'm doing. When I put these both together, what the colored versions are like the collection of both of those, and that's what the graph looks like. Like when I put it together, you can kind of see both of these together on top of each other. And what's colored is the graph of y equals 2 to the absolute value of x. And then like for this one here, it's the same idea. For this one here, if I were to graph this, what you should do is graph y equals 2 to the x minus 1 by itself, like without the absolute value. So without the absolute value, it has a horizontal asymptote at 1, or negative 1, I should say, and it crosses at 0, so it's going to kind of like go up, cross, and look something like this. So since you're taking the absolute value of it, whatever's below the x-axis gets reflected up. So this is all above the x-axis, so it's exactly as is. However, these points are below, so the absolute value is going to knock them above. It'll look like this until it gets to its horizontal asymptote at 1. So this will flip up and go like that, and you'll have a horizontal asymptote at y is 1. But what I have highlighted here would be a graph of the absolute value of 2x minus 1. Is that good? No problem. All right. Are there any other questions? Okay. So I guess that's it for today. Like I said, we can do another one on Sunday right before the test. I'm sure there'll be a lot of questions. But that's it for today, and I'll see you guys tomorrow. No problem.